All right, welcome everyone, and thanks for joining us for our tea talk today. Today we are fortunate to have Andrey Vayner joining us remotely as our speaker. Andrey is a postdoctoral fellow at the Johns Hopkins University and an expert in the role of quasars in the evolution of massive galaxies. And today he'll be telling us about gas flows in massive galaxies at cosmic new with integral field spectroscopy. So Andrey, take it away.
All right, thank you so much. Thank you for giving me the opportunity to talk today. So I'm gonna give an overview of my research over the last 2 or 3 years here, and then also try to conclude with some stuff moving forward, specifically with work with JWST that I'm really excited to be doing. Okay, so I'm primarily interested in trying to understand how massive galaxies form and evolve. And there's a lot of clues about how that happens from just looking at nearby galaxies. So I like to start with this somewhat motivational plot. So on the y-axis, what is being plotted is the percentage of ordinary matter that is locked up in stars in local galaxies. That's what this orange curve here, and it's plotted as a function of halo mass. And then if you look at what you would expect from just cosmology, this is the dashed curve over here at about 18.7%. But what you're actually seeing is significantly lower than this if you go to more massive and less massive halos. So for the more massive halos, it is thought that perhaps some form of feedback from supermassive black holes and stars is dominating this inefficiency in star formation. And then in lower mass galaxies, perhaps it's primarily dominated by star formation, although there's a lot of signs of evidence for even AGN helping with feedback even in the lower mass galaxies. So there's several feedback processes that cause this. It's hard to list all of them. I'm just listing some of the stuff that I personally think about. So this is by no means like a summary of everything that can potentially happen. But the main feedback processes that I think of in massive galaxies is, for example, stellar feedback from massive young stars, radiation pressure-driven outflows from AGN, jet-driven outflows in similar systems. So this, for example, 2 simulations, top one showing example of a jet-induced feedback where you have a jet slamming into the interstellar medium of a galaxy. And then the bottom one is you have an accretion disk wind that is initially driven by radiation pressure, and then eventually that wind slams into the interstellar medium of the galaxy and drives this this outflow. And each box here, the size here is about 1 kiloparsec, and the colors represent essentially the density of the interstellar medium in these simulated galaxies. On larger scales, you can have photoionization heating of the ISM and the CGM, circumgalactic medium, by quasars. And so that's another important mode of feedback, particularly on satellite galaxies at higher redshift. And then, of course, you also have ramp pressure stripping of nearby galaxies. Their interstellar medium essentially gets stripped by the hot gas of the intercluster and in the circumgalactic medium. And even at high redshift, it can potentially play an important role in driving feedback and the amount of gas that essentially falls onto the central galaxy. And similarly, there's a lot of feeding mechanisms. So this is processes of how you get the gas into the galaxy. And this is I really like this plot from one of the fire simulations. I think this is from the 2017 paper, focusing at where does the gas come from in the redshift 2 systems and redshift 0 and the redshift 2 systems. So on the right here, this is plotting different halo masses, and different colors here represent different mechanisms that are responsible for bringing gas into the galaxies. So I'm primarily interested in the more massive halos because that's where the most luminous quasars reside in the high redshift universe. And so you have several mechanisms that can bring the gas in these kinds of systems. You can have fresh accretion. This is gas that's primordial that accretes onto the host galaxy. It's at a very low, or has almost no metallicity. Then you have gas that gets recycled that was initially expelled into the circumgalactic medium by winds, but eventually falls back down. You can have transfer of interstellar medium as galaxies come close to each other. And so that's another mechanism that you can potentially bring gas into galaxies. And so what I'm really interested in trying to understand is how do the feedback processes and the feeding processes kind of regulate the growth of galaxies, and how do they balance each other to form the galaxies that we see in the nearby universe. One particular thing that I'm interested in is understanding how we have these really tight correlations between, for example, the mass of the supermassive black hole and the velocity dispersion of the bulge in a galaxy, or the mass of the black hole and the total mass of the bulge. These are very tight correlations, but from a standpoint of gravity, the sphere of influence of a supermassive black hole is very tiny compared to the sizes of these correlations, the physical sizes where these correlations occur. And so it's this processes from feedback and from accretion of gas onto galaxies that I think balance each other in some way to form these relationships. And so I'm really interested in trying to understand how all these processes occur and how we can potentially explain these strong correlations that we see in the local universe. But of course, majority of the formation for both black hole growth and stars happens in the distant universe. So on the left plot here, this is plotting the star formation rate density as a function of redshift or look back time. And we know that primarily majority of the star formation happens in the distant universe, so between redshifts 1 and 3. That's where majority of the star formation occurs. Interestingly, that's also the redshift range where majority of the black hole growth occurs. And so if we want to understand these feedback mechanisms and how the gas accretes onto galaxies and provides the fuel for both star formation and black hole growth, we really have to study distant galaxies. And we have to study these distant galaxies on different scales. And so this is what a project that I've been working on since the start of the academic year, trying to bridge these different size scales and trying to better understand how the gas feeds into galaxies and how that loops back into the surrounding circumgalactic medium. So on the left here, I'm showing a typical field of view of Hubble Space Telescope imaging capabilities in the near infrared. And then, so this is a field centered on one of the quasars that I've been studying. And then the smallest scales are probed by Keck adaptive optics with interior spectroscopy from the OSIRIS instrument. So that's the yellow box here in the middle highlighting the tiny field of view that really probes the highest spatial scales and closest separations to the quasar. And so we've targeted about 10 quasars to study their host galaxies in nebular emission lines such as H beta, oxygen 3, H alpha, nitrogen 2, and so forth that are redshifted into the near infrared. And we're doing these observations at a spatial scale of about 0.1 arcsecond resolution. And so the goal of this project was to detect ionized outflows on galaxy scales, study the interstellar medium finalization mechanisms, and detect extended emission on 8 to 30 kiloparsec scales. And this was a huge part of my thesis when I was at UC San Diego, and it got published in 2 papers last year. The other thing towards the end of my thesis is I was very interested in trying to also bridge the gap with these observations between size scales of the interstellar medium and the circumgalactic medium. And so we did go back and re-observe some of these targets in a special mode with OSIRIS where we're using bigger pixels to try and get more sensitivity to more extended emission. And I'll show you some of that data in a few more slides. And then, so for the larger scales on the circumgalactic medium, so this is now the yellow box, this is roughly probing scales on 100 kiloparsecs. We really want to study the results in the circumgalactic medium in rest frame EV emission lines, such as Lyman alpha carbon 4 and the helium-2 1640 line. Specifically, the focus here has been on this helium-2 line, which is a recombination line, and we want to use it as a newer probe of the gas kinematics and mass measurements of the warm ionized gas in the circumgalactic medium. This project, we're also trying to see if we can detect evidence of feedback on satellite galaxies. Of course, we want to detect those galaxies too to quantify the overdensity in these systems. Are these quasars in protoclusters or are they living in protogroups? So KCWI is supposed to help us try to understand the immediate environment of these systems. And so we basically selected a few targets where Lyman alpha and helium-2 falls in sort of the most ideal window in terms of sensitivity of the instrument. And we went with very deep observations on a few sources to try and get this multi-wavelength deep observations to really try to get a picture of what's going on in these systems. And as I'll show you in a bit, while the focus has been on the helium-2 line, Lyman alpha has been very interesting in these sources as well, and has given us some information about the 3D structure of the circumgalactic medium. And so that was an interesting result that I'm going to share with you in a second here. And on similar scales to KCWI, we've also obtained ALMA observations, which is an interferometer that can study the molecular interstellar medium at relatively high spatial resolution, somewhat similar to what we can obtain with OSIRIS. And the goal of that program was to search for molecular outflows, but because the field of view of ALMA that's shown here in the yellow matches that of KCWI, we were able to actually study the molecular gas properties of the same satellite galaxies that we see in KCWI that are perhaps in the surrounding circumgalactic medium of the quasar host galaxy. So this synergy between ALMA and KCWI has been very powerful in the two sources that I'm about to show. We've been very fortunate to be able to do this sort of science. Okay, so the two galaxies that I've been studying for this project, this is their extended Lyman alpha emission that we detect on 100 kiloparsec scales. So this is integrated Lyman alpha intensity that's being shown on the left and the right here. The bar represents 86 kiloparsecs in both of these systems, and then the ellipse here shows our resolution, which is about 8 to 10 kpc essentially in these systems. And we're able to probe to very faint surface brightness limits that just weren't possible before KCWI. And I don't really have to say too much about this instrument, given that it was built at Caltech. But really, the science that it enabled for the CGM has been amazing. And doing the science, also knowing the morphology and kinematics of the gas on the galaxy scales from OSIRIS has been very incredible. So these two systems are very interesting because the radial velocity maps show a very nice gradient feature of two kinematic components, one that's redshifted, the other one is blue shifted relative to the systemic velocity of the circumgalactic medium. And it's very similar to what you see in some of the hydrodynamical simulations of relatively massive halos at high redshift that also show these multi-kinematic components that in some cases are primarily blue shifted and red shifted. And so we want to understand better these kinematic components and really try to understand whether this gas is inflowing or outflowing and how much of it is available to fuel future star formation. So similar kinematics maps are produced for the helium-2 line, but the issue is that this line is very faint. So it's about 10 times fainter than Lyman alpha. And for one reason or another, has been primarily only detected in the radial loud quasars. So these objects that I'm showing you here are very luminous blue, typical quasars at high redshift that are also very radial loud. And so these are the systems that historically have been showing helium-2 emission, and with KCWI, we were able to actually map it on circumgalactic medium scales. And because it's a recombination line, it doesn't have these difficulties that Lyman alpha has. And so we were able to get a better estimate of what the systemic velocity is for the gas in the circumgalactic medium. And so we're able to make accurate measurements of the motions of the gas using redshift measurements from the helium-2 line. So given that the data has really high signal to noise, we were able to detect Lyman alpha to very large extents. And we were able to get enough signal to noise on the line in individual spectral pixels at large separations where we can actually map both the emission and in some cases the absorption component of the line. And so in this particular source, that enabled us to understand better what the 3D structure is of the circumgalactic medium. So on the right here, this is again just showing the integrated intensity map of Lyman alpha for the source. And then now the contours here are separated into two blue and redshifted kinematic components that we were able to identify in the radial velocity map. And we basically integrated all the pixels to build up enough signal to noise to see what the line profile is at high enough significance where we can actually do accurate modeling of both the emission component, which is shown here in green dashed line, and then the absorption component that we detected that you can see in absorption over here at about roughly 500 kilometers per second. What's interesting about this absorption component is that it almost exactly matches the velocity of the redshifted kinematic component in this particular system. So that gives us a bit of a clue of what the 3D structure might be and what's located in front of what. So the absorption is on the blue shifted kinematic component, and it's at almost exact same velocity as the redshifted component. There's some variation, but it's all within the consistent with the individual motion of the gas that you detect in individual spaxels in the data cube. So what we decipher from this is that the redshifted component is in the foreground and is moving inwards, while the blue shifted component is likely in the background and is also moving inwards towards the quasar host galaxy. And so this kind of confirms that the kinematic structure that we saw in the radial velocity map is consistent with a scenario where this gas is likely inflowing onto the quasar host galaxy. But specifically, what we found actually is that it's likely accreting onto a group of galaxies. So the question is, what is exactly the gas accreting on? And so we think it's a group of galaxies. So on the left here, again, this is the integrated Lyman alpha intensity map. And then now the orange stars here are 3 companion galaxies of the quasar host galaxy that we were able to identify through this multi-wavelength analysis. So they're detected in lines in carbon monoxide with ALMA, and they're also detected in ionized lines with, for example, with H alpha and oxygen 3. So we know that they're at the redshift of the quasar host galaxy. So this on left panel shows sort of the large scale view. Again, the bar here is about 80 kiloparsecs. Then if we zoom in on this galaxy group in the background, this is stellar continuum rest frame of about 5,000 angstroms that was observed in the near infrared. And you can see that the 2 orange stars here are associated with 2 galaxies. And then there's a third galaxy here that's merging with the quasar. The white contours are the highest spatial resolution that we were able to obtain with OSIRIS. Unfortunately, the resolution of the continuum data from Hawkeye just wasn't good enough to actually see this quasar, this companion galaxy, just because it's too close to the quasar. The quasar in this image has actually been subtracted out. And then the red contours here are OSIRIS observations where we went back to this particular object and try to see, can we see structure on larger scales? So this is going back with a coarser plate scale and going deeper and trying to observe the sort of the gap between CGM and ISM for this particular galaxy. And then here, the far right image is really just zooming in, and this is in the background. This is HST wide field planetary camera 2 imaging in the V band. Essentially, you can see some light from the quasar host galaxy, some UV light from the quasar host galaxy, and also a portion of the light from the merging galaxy that's closest to the quasar. And so you can see that likely this extended emission that we see in Lyman alpha is probably accreting onto this group of 3 galaxies plus the quasar host. So we were able to make some rough estimates of how much gas there is in the CGM. So we think there's about 0.5 to 3 times 10 to the 10 solar masses of warm ionized gas within 30 to 50 kiloparsecs from the quasar. And this measurement was done using the helium-2 line. We've also done this measurement with Lyman alpha, but there's some complexities there about assumption of whether how much of the line flux comes from recombination versus how much of it comes from resonance scattering. So it makes the computation a little bit more complicated. And then we were able to estimate roughly that the inflow rate is on the order of about 50 to 100 solar masses per year. Again, this is probably just an order of magnitude estimate, and that's just using the dynamical time scale of the gas within 50 kiloparsecs. What's interesting is that this inflow rate is comparable to the outflow rate that we measure both from the molecular gas and the ionized gas observations. And again, these numbers are basically on the same order of magnitude. Studying the outflows has been probably a little bit more challenging because galactic outflows are inherently multi-phase. And so essentially what that means is that their energetics are divided among the different phases, among different gas phases. And this is hydrodynamical simulations from Richings et al. From last year that really highlights this, this multi-phase nature of galaxy outflows. And so on the x-axis, this is different emission lines that you can use to probe galactic outflows. And so this goes all the way from molecular gas from carbon monoxide all the way to really high ionized gas from for example, oxygen and neon over here. And so you can see that this in black here, this is what you see is the different energy and momentum rates that you can see in these different lines. And so if you really want to get a picture of the energetics in galactic outflows, you can't just study a single line. And so for my work, I've been primarily focusing on studying these outflows in combination of near-infrared emission lines, or well, lines that are retrofitted into near-infrared, for example, H alpha and oxygen 3, and then in the molecular gas using carbon monoxide, using ALMA. So this is sort of just a summary result from studying the multi-phase outflows in the system. So this is from a paper that I published last year. So in background, you can see integrated intensity from the CO line, using the 4:3 or the 3:2 transition in these systems. And then the pink contours represent molecular outflows that we detected either through very broad disturbed gas in these systems or high velocity gas relative to the systemic velocity of the quasar-host galaxy. And then in contours in white, that's the ionized outflows in these systems that we detect with OSIRIS. And the bar in each one of these is about 1 arcsecond. And again, the ellipse is just the point spread function of the ALMA observations. So the source that I was talking about previously is this one here. What's really interesting about this object is that not only do we detect a molecular and an ionized outflow in the quasar-host galaxy, there's also a molecular outflow that's ongoing in the nearby galaxy that's merging. And so it's interesting to see that there's feedback processes happening in this particular source, both in the quasar-host galaxy and in a nearby system. So it's ongoing during the merger in this particular object. And so I thought maybe I could highlight what's going on in the source with this animation here. So it starts off with the Lyman alpha emission in the circumgalactic medium. Then it goes to show the velocity structure in the CO4-3 line that we detected with ALMA. And then it'll finish showing where the location of the ionized outflow is in the system from OSIRIS. And again, the stars here represent those 3 galaxies that are part of the group, and then the white star represents the location of the quasar. And so again, I just wait for it to finish here, but it shows the multi-phase nature of the gas in this particular system, both from inflowing and outflowing gas. And yeah, so it's a complicated system. And so I've been working on a diagram that's trying to sort of explain what's happening in the system. So the white contours here is the low surface brightness that we detect in Lyman alpha. We have the backside of the inflowing component, which is from the blue shifted region that's in the back. And then we have the front, which is the redshifted kinematic component. And then we have the outflow from the quasar-host galaxy that's pointing sort of in to the left here. And then we have an outflow from the merging galaxy in the upper left that's also happening while there's an ongoing merger. And so I guess what I'm trying to highlight here is that these systems are very complicated, and there's ongoing mergers, feedback from likely from the supermassive black hole. We think that's what most likely drives these outflows in these systems. We don't think star formation alone can do it. And then you also have inflowing gas from the circumgalactic medium happening all at the same time. So you're really watching a massive galaxy here form by studying all these different multi phases on different spatial scales. And so we're really trying to tell a story on the individual sources here by combining this multi-wavelength data that's been taken over many years of observations. All right, so just to summarize the circumgalactic medium science that I wanted to highlight in the talk. So we combine KCWI, OSIRIS, and ALMA observations to study the circumgalactic medium and the immediate quasar environment. Two systems, we detect extended Lyman alpha emission, helium-2 and carbon-4, again on CGM scales. And then studying the absorption and emission profile of the Lyman alpha line allowed us to decipher the 3D structure of the CGM. We detect signs of gas inflows in both objects, and we also detect outflows in these same systems. We detect gas that appears to inflow on a group of galaxies near the quasar host. And while I don't have time to talk about both of these systems, the storyline is somewhat similar for both. Okay, so for the next part of the talk, I wanted to highlight my work on extremely red quasars, which is this somewhat newly discovered group of objects that I've been studying over the last 2 years or so. And I'm really excited for the James Webb Space Telescope observations that we're going to see for some of these systems. And so I just want to highlight some of the science that is coming our way, and also the science that we've been doing so far. So why study obscured quasars? And the idea here is that we think that you can couple the energy from the accretion disk around the supermassive black hole to the surrounding dust a lot easier in obscured systems than in others, and you can drive relatively efficient outflows. This is an example from a hydro simulation on the left here, showing the kinetic luminosity, essentially the energy rate of the outflow as a function of radius from the supermassive black hole. And then the different lines here basically show how much energy rate you have at those radii. And you can see that in the simulations, they can couple about 0.1% of the quasar's volumetric luminosity to these outflows. And that's sort of a key value in these simulations, where they can say that these outflows actually have impact on the quasar on the quasar host galaxies. And so the punchline is that heavily obscured environments are excellent places to drive outflows on dust grains. And then on the right, it's a similar plot, but just looking at the momentum flux in these systems. And again, they're able to couple both the energy and momentum in these obscure systems relatively well. So extremely red quasars, what are they? I mean, it's in the name. They're just they're really red if you look at their colors between optical and infrared. And so that's exactly how they're selected. So they're I-band minus Y's 3 filter magnitude is greater than 4.6. So this, if you look at the color magnitude diagram, or sorry, the color diagram, you can see that they're basically shown to be extremely red objects, so which live in sort of the upper portion of this diagram. In some cases, they're also red in the mid-infrared as well. Or rest frame, this translates to basically near infrared wavelength. Then the other criteria for selecting the core sample of the extremely red quasars is that there was this additional criteria that the carbon-4 emission line equivalent had to be greater than 100 angstroms. And the idea here was to select objects that have very, very strong emission, but very weak continuum. And so the idea there was to try and maybe select more typical type 2 quasars. But as I'll show you in a second, these objects look nothing like your typical type 2 quasar that you sort of classically saw before. So here's the spectrum stacking a large sample of the extremely red quasars detected in the Sloan-Digital Sky Survey. So this is Fred Hammond's paper from 2017 that really discovered these objects and really try to put them in context with the other quasar population sample. So the black line here, that's the extremely red quasars. You can see that they have very peculiar emission line ratios compared to blue quasars that are shown here in the red and and the green that are matched in essentially in bolometric luminosity to the extremely red quasars. So one thing to notice, for example, the nitrogen 5 line relative to Lyman alpha has a very drastically different ratio than what you see in typical blue quasars at redshift of 2, essentially. The other interesting thing is that extremely red quasars have a very peaked emission line, so there's not a lot of flux in the wings of the emission line that you typically see in more typical quasars at these redshifts. What was surprising to also see is that a number of these sources showed outflows in absorption, and I mentioned that these sources do not have very strong continuum emission, and so it was very interesting to see that you can detect outflows up to almost 9,000 kilometers per second in absorption in the rest frame UV spectra of these systems from the Sloan Digital Sky Survey. Once near-infrared spectra was taken of these sources, the story got even more exciting and complicated, I guess. So this is work by Nadia Zakhamska from 2016. This is getting the first near-infrared spectra of these objects. So this is looking at rest frame optical lines. And what you can see here in pink, this is supposed to be H beta and the oxygen 3 doublet. And the lines are so broad in these systems that the oxygen 3 line almost blends together. So these are really high velocity outflows, very disturbed gas in these systems that you don't see in essentially any other quasar sample at low or high redshift. And so my interest immediately when I saw these spectra was, we have to resolve these outflows. What scales is this fast moving gas on? That was my biggest question. And so last year, we were able to publish a paper on a number of these extremely red quasars, looking at them with integral field spectroscopy and adaptive optics, so trying to get to this 0.1 arcsecond resolution and really try to resolve where these outflows are happening. And so in this one particular source, we were able to resolve that these fast moving gas is actually on galactic scales. So in this case, we detect the outflow almost out to 4 kiloparsecs from the quasar. Again, the quasar here is shown with a white star. The quasar itself has been subtracted out. And you can see this extended emission on host galaxy scale. We also detect some narrow emission in this particular object, and that could either be from a star forming region or a tidal tail feature. It's kind of hard to decipher, but the punchline is that we think that these outflows had to be driven in relatively obscured environments for them to look the way that they do on these kiloparsec scales. And so we definitely think that perhaps radiation pressure on dust grains in these systems played an important role in the small scales to actually drive these powerful outflows. So we also, we basically try to point every single telescope that we can at these systems, both from the ground and space. And so one interesting project was to try and see if we can detect X-rays from these systems. This was a little bit ambitious given that we knew from the Sloan Digital Sky Survey spectroscopy that these systems are likely quite obscured. And so on the left here, this is a spectrum, if you want to call it, by combining data from XMM and NuStar. And you can see that we did not detect a whole lot of photons, but that confirmed that these objects are, in fact, almost Compton thick, so very high column densities of about 1 × 10⁻⁴ particles per cubic centimeter. But it also confirmed that these are indeed very luminous quasars. I mean, we sort of already knew that from mid-infrared observations, but seeing this also in the X-rays really confirmed that they're both highly obscured and very luminous systems. And essentially fitting the model to the X-ray data, this is work done by Yuzo Ishikawa, who's a grad student here at Hopkins, really confirmed that these are super Eddington, extremely rapid accreting supermassive black holes at high redshift, at redshift of 2. And we've been able to detect them in Sloan up to redshift of 4. I think the highest redshift is 4.6. And the challenge there is just we have to go to longer wavelength in the mid-infrared to do the color selection, but indeed we are able to detect these sources out to relatively high redshifts. Okay, so there's more surprises from these sources. So this is looking at one of the particular sources that I showed previously, where we're able to resolve the extended ionized outflow in the system. So the top here is a spectrum taken with LRIDs on Keck, using polarization observations. And what you can see is that the continuum is highly polarized, up to almost 15%. This is pretty crazy. You don't often see this in quasars, and you don't often see this in radio quiet quasars. So that was a bit of a surprise. This work by Rachel Alexandra from 2018. The other thing is that you also see that the emission lines are also polarized. And so just this really intriguing result. And then we got UV imaging, rest-frame UV imaging from JWST at similar wavelength range to the LRIS observations here, to try to see, can we see the scattered light spatially? Can we resolve it and see where it's located? And the sources just keeps on giving. And so on the left here, the dashed line shows the scattering angle from the spectropolarimetric observations. There's basically a prediction how the direction of how the light is supposed to scatter. And what's interesting is that, so in the red contours here, this is the ionized outflow in the source. And we see that the ionized outflow follows the same direction as the scattering angle. And then in the background, this is rest frame UV emission that has been PSF subtracted from Hubble. And you can see that there's extended UV emission on similar scales. And this is likely light that has been scattered off the dust grains, probably close to the quasar actually, and basically diffuse in the same direction where the outflow is happening. So the punchline here is both the photons and the gas is diffusing in the same direction in the source. So that was a very, very exciting result. We tried doing this for some other sources, but the sensitivity is just is not always there. And we hope that maybe deeper observations in the future can do this. But this source specifically, we were able to see very clearly. So we have a sort of a schematic diagram of what's happening in this object. So we have an obscuring either torus or a combination of torus plus extended emission from the host galaxy. We have the outflow that's close to the polar angle here. And then we have some scattering that's happening off dust grains near the vicinity of the supermassive black hole, which is in the center here. And the light and the outflow basically diffuse in the same direction. And so our line of sight is relatively close, looking through the obscuring material towards the center of this galaxy. So we're really interested by these sources, and we want to explore them more. And so we have a cycle 1 geo program that I'm leading, and the goal here is we will want to observe 5 extremely red quasars with the fastest moving outflows detected in the oxygen 3 5007 angstrom line. We were approved for about 10 hours on source, total of 21 hours for the program. So the goal is we just want to see simultaneously, observe simultaneously a bunch of nebular emission lines and really try to resolve the extended emission down to unprecedented surface brightnesses in the near infrared that we cannot do from the ground because of the background. It's just too strong. And so we're really hoping to push the limits here with JWST with these sources. Of course, JWST also provides very good resolution of these wavelengths. And so it'll be interesting to both spatially resolve it and map it to those surface brightnesses. And so our science goals are very similar here to what we've been doing. We want to measure the outflow sizes, rates, dynamics, and so forth. And really interested in understanding better the emission line ratios in these sources, searching for evidence of shock heated gas, for example, and trying to correlate where the shock gas is happening relative to the star formation. And of course, JWST will be sensitive enough to actually detect the stellar continuum in these objects at small separations from the quasar, which is really exciting, something again that we just couldn't do previously. So this is just sort of a summary showing the spectra of these 5 sources from near infrared, again, just showing that the emission lines are very broad. And on the right here, this is the oxygen 3 velocity width as a function of quasar luminosity. Then the gray points are your typical blue quasars at high and low redshift, and then the red squares here are the extremely red quasars. And so you can see that they are sort of in their own portion of this diagram here. And so we're just really excited to see what they look like with JWST. We know that some of them are already spatially resolved. This is from Nadia's work from 2019, looking with Hubble, and we're actually able to resolve the quasar host galaxies in stellar continuum. And so we're excited to do this now with JWST. We're also going to study some of these quasars in an early release science program that's called Q3D. It's a program that has about 22 members in it, and the science goals is really to study massive black holes at high redshift, feedback science, similar to what I've been mentioning here. And it's allocated about 17 hours. And we're basically going to use both the near spec IFU and the meteorite IFU, and we're going to cover all the modes and try to test high contrast science at high redshift. So we're going to study 3 sources, being redshift 0.4 to 2.9. With near spec, we'll cover ionized gas traced through recombination lines of hydrogen, molecular gas through rotational and vibrational lines of hydrogen at mid-infrared with MIRI. We'll also detect dust emission through pH emission, and we have lines that are specific to shock indicators for the feedback science. And the source that I've been showing previously is the highest redshift source that we're going to observe. And so we're really excited for the new data and sort of maybe provide a different view of what this galaxy looks like with JWST. Part of the program is we're also developing a software package called Q3D Fit that will do PSF decomposition to detect faint extended emission. It'll provide radial velocity, width, and intensity maps for each line that you're trying to fit, which will hopefully give you information about the dynamics and the kinematics of the interstellar medium. And we also want to study emission line ratios, and the software is being developed to do that, and specifically optimized for JWST observations. And a lot of it is based on this IFS-FIT package by David Rupke from 2017. We're translating it into Python. We're making it as easy as possible for the user to use. And so a lot of it can be run from example, from a Jupyter notebook, and it will be available to the community before the call for cycle 2, but we've already had users test it last week or 2 weeks ago now in a JWST webinar, and I think those videos will be available online. So if somebody's interested in learning what this software does and how it works, just reach out to me and we can set you up with it. We're also trying to make this software usable with other ground-based instruments, not just JWST, even though that's where it's being optimized. But we have tested it on data sets, for example, like KCWI. And so it is possible to use the software on other instruments. Just to quickly show how the software works. So this is looking, the animation is just basically looking at different spaxels in the data cube of the simulated data. The bottom panel shows the fit to the unresolved component from the quasar. And then the top panel shows a combined fit both to the unresolved and to the extended component. So the purple emission lines here, this is extended gas from the host galaxy. And so we're able to essentially decompose the resolved and unresolved component in the simulation. So just to summarize here, extremely red quasars is an interesting class of objects that may be experiencing powerful feedback events during the long sought out blowout feedback phase that we've been really trying to detect over the last decade or so. We have an early release science program that will study 3 obscured systems and develop software for high contrast analysis with space-based IFS observations. We also have a cycle 1 geo program that will specifically look at extremely red quasars, and we're developing this Q3D Fit software to do the PSF subtraction that's optimized for JWST data. And the goal is we want to produce high-level science-ready data products for the community. The software will be tested again on these 3 systems, but it will be released before that to the community. So if you have any questions about it, just shoot me an email here, and we can see what we can set you up with. So thank you for your attention.
Okay, thank you, Andrey. If anyone has any questions, please raise your hand or feel free to type them in the chat and I can relay them to Andrey. Okay, I see Peter, go ahead.
Really interesting work. I'm excited to have the chance to look at some of this in more detail. You said, I think you were talking about 4C, the 4C source in particular, that it was really complicated, and you definitely impressed me with that. And so I wonder if you could just say a little bit about, you know, with multiple systems, what would be the kind of patterns, or, you know, what are the trends, or, you know, what kind of things will you be looking to make this subject less about every individual object and more about understanding more broadly the role of inflow and outflow in if you could comment on that.
So I think the idea there is that we have a few more of these systems. It just takes a while to, if you look at it in the individual systems, to kind of build up a picture of what's happening. But we do have these essentially 10 objects where we can do similar analysis. And we also have a program where we want to expand this to a larger sample of KCWI data that's sitting in the archive, and to really try to build up a larger sample and look at statistics of what's happening in these systems more broadly. I think there's been a lot of work done on studying the Lyman alpha emission in spatially resolved manner, but I don't think a lot of people have taken into account that you can actually see the absorption, self-absorption in some of these cases. And that really gives you this 3D picture in certain scenarios. And I think doing that for more systems could give us better clues of how the gas is moving and how often is it outflowing versus inflowing versus outflowing. And I think that's just going to take some time to build up, doing this analysis carefully. But we do have a plan to extend this to essentially 8 more systems. 2 are done, 8 more systems for the radial out sample, and then we want to do this eventually for the extremely red quasars too. We're actually hopefully obtaining data next month for these systems, and to try to build up a better sample of what's happening both in the host galaxies and in the CGM. Yeah.
Next month, actually, so in May.
Yeah.
Wow. But this is not JWST within May, no?
No, so the JWST data we're hoping will be taken in the fall, but these are the same sources. So we'll get KCWI data for the same sources that we're getting.
Right. Sorry, I misunderstood. Thanks.
Are there any other questions at the moment for Andrey? Okay, I don't see any others. So I will stop the recording here, but feel free to stick around if you have other questions or want to chat to Andrey. And thank you again, Andrey, for the great talk today.
Thank you so much.